Greetings everybody. This video will hopefully explain how to draw in the tension force. Again, to summarize, do a little quick review. Right now we're in Chapter 4, and our goal right now is simply to understand how to draw in what I call the four most common forces. There are other forces that we'll run into, but the four most common are weight, normal, and tension and gravity. Well, in the previous lecture, we covered how to draw in the weight and the normal force. And remember, any object in the Earth's atmosphere experiences the weight force, the force due to gravity. The magnitude of that force is given by mg, where m is the mass of the object and g is the acceleration due to gravity, 9.80 meters per second squared. And notice, no matter the orientation of the surface on which the object sits, or it doesn't even have to be on the surface. Notice here the weight of the man, mg, straight down. Here, a skier on an incline. How do you draw the weight force? mg. Notice in both cases the mg vector is clearly in the negative y direction. Notice here's a bug on the surface of a bowling ball. The weight of the bug, mg. Notice in each case the vector is clearly in the, I've taken great care to draw the vector in the negative y direction. Now, sometimes, again, we use the letter W to indicate weight. So you can either label it with a W or an mg. I prefer mg, but once in a while you'll see where they call it W. So notice here's a basketball. Although it's in the air, and irrespective of whether it's going up or coming down, the basketball is an object in the Earth's atmosphere. It experiences a weight force. Notice no matter where the ball is, what's the weight? Here, W, W, W. Notice in each case the red vector representing the weight is in the negative y direction. It's the same magnitude no matter where the ball is. The ball could be rolling on the floor. It could be at rest on the floor. It doesn't matter. Notice in each case, weight, 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 weight. So W is equal to mg always. Just a quick review as to how to draw the weight. Now, what about the normal force? Well, remember, a normal force occurs whenever an object is in physical contact with a surface. It's also sometimes called the contact force. It is a pushing force. It's the force of the surface pushing on the object. Remember, Fn is always perpendicular to the surface upon which the object is in contact with. Now, as we'll see in the very next page, the direction of Fn depends on the orientation of the object and the surface. In other words, it depends on the geometry of the problem. Well, let's look at these three cases. In the first case, there's a person, standing on a horizontal surface. You could be standing on the street corner waiting for a bus. You could be standing in line at a movie theater. Doesn't matter. You could be standing on the floor in a room just reading a sign. Who cares? But notice the object is physically in contact with this horizontal surface. Ergo, normal force. It's the force of the surface pushing on the object. It's this green vector Fn. Notice the green vector, it originates from the surface and it's pushing it. You draw it through the object and notice it's pointing away from the surface because it's the force of the surface pushing on the object. Notice if you look right here, this Fn vector is clearly perpendicular if you look closely right here, this green vector Fn is clearly makes a 90-degree angle with this surface, with this horizontal surface. And of course, mg is the weight of the person. Now let's go over to the right. Let's look at this skier skiing down a slope, i.e. it's an object in contact with an inclined surface. Normal force, the skier is in contact with the slope. Fn, notice again my Fn vector, if you look closely, it clearly is drawn such that it makes a 90-degree angle with the incline. So if you look right in there, that vector Fn clearly is perpendicular to the incline. Remember, in the language of math and physics, normal means perpendicular. And again, every object experiences the weight force, mg. Nothing complicated. The weight of the skier is, notice mg is in the negative y. Well, let's look at the ubiquitous bug and the bowling ball. Again, the bug is in contact with the bowling ball, ergo the bowling ball will exert a normal force on the bug. Notice this blue dotted line, that right where the bug is in contact with the bowling ball, that blue dotted line is tangent to the bowling ball, right at that point when the bug is in contact. The bowling ball pushes on the bug with this normal force Fn. Clearly, the normal force Fn, notice if you look carefully, it's clearly perpendicular to the tangent line to the bowling ball at that point, meaning Fn is perpendicular to the bowling ball at that point where the bowling ball and bug touch each other. And notice again, that's what we mean. Normal means perpendicular. The normal force is the force of the surface pushing on the object, and it is perpendicular to the surface. That's why these three cases illustrate that Fn depends on the geometry of the specific example, of the specific problem. Okay, that was a quick review of Fn and mg. Now let's go to tension force. Well, you have a tension force, and that's the third of the four most common forces. You have a tension force whenever an object is connected to a rope or a string or a cable. So I'll use those three terms interchangeably. So if I say rope, it also applies to a string, it also applies to a cable. And with the tension force, we're making the assumption that the rope, string, or cable does not stretch. So it is unlike a spring or a rubber band. Those are different forces, which we'll get to later. So we'll assume that the rope, string, cable doesn't stretch. Well, tension force is a pulling force. It's the force of the string pulling on the object. We use a capital T to indicate tension force. And it's, remember the little arrow above it, that's the standard math and physics symbol telling you, hey, this thing with the arrow above it, it is a vector. So this is saying that the tension force T is a vector. Just like, again, so tension, it's a vector. Now again, to draw the tension force, it's always directed along the string and points, and it's away from the object. So in a way, it also depends on the geometry of the problem. Notice here what I've done in this figure. I've connected this car, I've attached to a string to this car, run the string over a frictionless pulley, and attached the other end of the string to what we call a falling mass. We'll run into these types of examples in the next lecture. If I release this mass from rest, gravity is going to cause it to accelerate straight down, and in doing so, because they're connected, that falling mass will pull the car up the incline. So we call that the falling mass. But we'll get into that later. Main thing, car and mass, both attached to a string, and they're connected via this frictionless pulley. Well, again, typically we draw all the forces acting on the object. So let's look at the car. Well, it's resting on this incline, so there's going to be a normal force, just like the previous example with the skier. Notice Fn, that's the normal force. That's the force of the ramp or the incline pushing on the car. Again, clearly Fn is clearly perpendicular to the ramp. Again, there's the weight, mcg. I'm calling it mc, meaning mass of the car. That's the weight of the car. Notice clearly it's drawn in the negative y direction. Now let's look at the tension force. Well, remember, the car is connected to the string. Tension force, it's the force of the string pulling on the car. Remember, you draw it along the string, and it's always directed away from the object, and we label it T. So that red vector, that's the tension force acting on the car. Now let's look at the falling mass. Again, string attached to the car, tension force on the car, string goes over the frictionless pulley, then it's attached to this falling mass. Well, again, we want to draw all the forces. mg, that's the weight of the falling mass. And again, I should note clearly, if you look here, the falling mass is not touching the incline whatsoever. There's a clear gap, so it is not in contact with any surface. There's absolutely no normal force acting on the falling mass. But the mg, that's the weight. Now again, the string is connected to the car, runs over the frictionless pulley, it's connected to the falling mass. Tension force, object connected to a string. How do you draw it? It's directed along the string, but away from the object. So this right here, this tension force, that's the tension force. That's the force of the string pulling on the falling mass. Again, along the string and away from the object. Along the string, away from the object. Now you might ask, well, Dr. Gomez, the two masses are different. MC is the mass of the car, M is the mass of the falling mass. You might say, well, Dr. Gomez, if those two masses are different, how come they have the same tension force? Well, that's because when you connect two objects with a string via a frictionless pulley, if the pulley is frictionless, which is the only case we're going to have to worry about for the time being, whether or not the masses are the same, it doesn't matter. Those two tension forces will have the same magnitude. Naturally, they're in different directions, obviously, due to the geometry of the problem, but we know because they're connected via a frictionless pulley, the magnitude of those two tension forces is the same. And again, how do you draw a tension force? It's along the string, and it's a pulling force, so it's always directed away from the object. So you can clearly see this T, excuse me, that's the tension force exerted on the car. It's along the string, but away from the car. Now, frictionless pulley, we know the magnitude of those two vectors are going to be the same. Here, the tension force on the falling mass, along the string, but directed away from the mass. Now, we'll get into friction in the next video. I want to keep the size of this video manageable. So let me go ahead and save this video and get it posted.